All right, everyone, welcome back. I've applied the configuration. However, I did make some changes. Now, because these links are point-to-points, okay, and because each set of links is its own subnet/broadcast domain, I decided to modify the IPv6 address space to reflect that. So if you notice any discrepancies, it's only because I've subnetted the IPv6 address on the interfaces to better reflect the IPv6 point-to-point subnet broadcast domain better. And if this address and how I subnet it doesn't look familiar to you, I would recommend reviewing an IPv6 video that I do have on our channel to understand this a little bit better. Okay, so moving forward, I wanted to show you my EIGRP configuration, and here it is. All right, so it's a very basic EIGRP configuration. I thought I'd start off with IP version 4 and then we'd move towards IP version 6, even though we've laid the foundation to support EIGRP version 6. We'll begin with IP version 4 because it's just better to kind of understand. So there's a couple of things that I wanted to show you. So over here, you'll notice that I purposely shut down or paused the Gigabit Ethernet 01 interface on Acme Edge 2, going down to Acme Core 2. The reason I did this is because I would like to do some packet analysis with you. But before I turn the link back on, I just want to take a moment and talk about how EIGRP calculates its metric. All right. Now, with any routing protocol, it doesn't matter what we're talking about, they have an administrative distance and a cost associated with them. Now, an administrative distance is basically a ranking of trustworthiness between various routing protocols. And you could have multiple routing protocols operating on a single router, but what differentiates them in their trustworthiness is the administrative distance. So for example, if we take a look at this chart, a connected interface is more trusted than a static route, and a static route is trusted than a summarized EIGRP route, which is more trusted than a BGP route. And the list goes on and on and on and on. So if you have a connected route and you're running OSPF, the connected interface will always be selected or have a better precedence than OSPF. And if you had a route that was learned via EIGRP and a route that was also learned the same prefix via OSPF, EIGRP would be considered a better choice than OSPF, just because of its administrative distance. Now that we've talked about and covered EIGRP's administrative distance and what it means, let's talk about how and what it uses to determine best paths to destination networks. So EIGRP uses 5 variables, okay? Bandwidth, delay, load, reliability, and MTU size to determine cost. And the cost is essentially a routing protocol's method for determining a best path to a destination network. Now, even though EIGRP could use load, reliability, and MTU size, only bandwidth and delay are the defaults. So bandwidth, delay are always going to be used. And it's not recommended to add these other variables like load, reliability, and MTU size only because it could result in frequent calculations of the topology table, and that's something you really want to avoid. So where does EIGRP obtain these values anyways? Well, let's take a look. So if we go into Acme Edge 1, and I do a show IP protocols, for example, you'll see that under the heading of EIGRP 1528, that the metric weights are listed here in K values. So bandwidth, delay, load, reliability, and MTU size. If I go one step further and I go interface 00, you can see that the values are located under the interface. So when it's actually going to be applying that dual algorithmic calculation, it obtains the values directly from the interface. Now, why is that important? Because there was an excellent slide in our notes, because EIGRP has embedded in itself the ability to determine what type of media is connected to the interface. And dependent on the media that is connected to the interface, it automatically assigns these delay values, which in essence modifies the dual calculation in the good and in the bad. However, there is a way of actually modifying these types of values. So for example, if I went into config t interface gigabit 00 and I typed in bandwidth 5000 and I redid the command, you'll see now that bandwidth is now 5000, which ultimately affects the calculation of EIGRP in determining the best path. So I have just effectively made this link less preferable when we do begin populating this routing domain with external IP prefixes. So what I'm going to do is I'm actually going to take that off. All right, so now that we've talked about EIGRP's administrative distance, 90, and the different variables obtained from the interface like bandwidth, delay, load reliability, and MTU size to calculate the best path to the destination, let's go ahead and turn on this link. Now, as you may have noticed, the link is already on, and the reason why it's already on is because when I tried to unsuspend it, my GNS3 application actually had a problem, so I had to restart it. So instead of actually using the suspend feature in GNS3, I'm just going to shut down and turn on the interface so we can take a look at what's going on. So I'm going to go on to Edge 2 and I'm going to do a shut, no shut, and let's see what happens here. So as you can see, I have just instantiated or instigated a disservice or a down, which caused EIGRP to re-establish an adjacency with its neighbor between Acme Edge 2 and Acme Core 2. And what you're seeing here are basically the different types of EIGRP packets that are used to form this adjacency. Hello packets with an acknowledgement packet, and most importantly, these update packets. And these update packets are what is used to actually begin building the topology database to which the dual algorithm is then applied to effectively then choose the best paths to these destination networks. Okay. You can also notice that the neighborships are formed on the multicast address of 224.0.0.10. And why don't we just go in and take a look now at these types of adjacencies and different types of tables. So if we take a look at the show IP EIGRP table, neighbor table, what we see here is that we have a repository of all the neighborships that this particular router has with regards to EIGRP IP version 4 packets or IP version 4 neighborships. So on the right here we have the IP address of the neighbor. So as you can see, this is Acme Edge 2 and this is Acme Core 1, the respective interfaces in which the adjacency is on, and the hold time, right? So one of the key things that we need to understand about EIGRP is that a hello packet is sent every 5 seconds out on an interface, especially an Ethernet interface. And the hold time is 3 times the hello interval. So if I don't receive a hello packet acknowledgement back in 15 seconds, I'm going to declare this host as down. So as a matter of fact, if I kept on going up arrow, you'll see that these values decrease, but then they repopulate back up. And what's happening is that it's the amount of time that the interface has not received a hello, and then once it does receive a hello, it then instantiates or restarts the timer all over again. So that's why you see it decreasing and then popping back up to 15. All right. Now these hold time variables differ depending on the interface to which EIGRP is connected to. And as I mentioned before, EIGRP has embedded within the protocol the ability to understand and determine what type of interface it's working with. And depending on that interface that it's working with, it will then adjust the parameters accordingly. So because these are Ethernet interfaces, it's 5 seconds of a hello interview and 15 seconds of a hold time. Okay. And also the uptime. So this is the amount of time that the neighborship has actually been up. So every single time an EIGRP relationship is created, or an adjacency is created, the entry will be in the show IP EIGRP neighbors. I would like to shift our attention to the IP routing table and the EIGRP topology table. Now, these two tables are intimately married to each other because the topology table collects topology information from its neighbors, to which it then applies the dual algorithm, and only the best paths are then selected or eligible to be inserted into the IP routing table. Okay, so if we look at the routing table of Acme Edge 1, for example, I can see that the routing table has been populated with EIGRP routes because of the letter D. Letter D means that this prefix has been learned via EIGRP. Now, there are two prefixes in this routing table we need to pay very close attention to because it's going to help us as we move along in this video. One is the loopback address that is directly connected to Acme Edge 1, 1111. As you can see, it's a directly connected route. So its administrative distance is 0, which trumps the administrative distance of EIGRP, which is 90. That's why you're never going to see a D for EIGRP, because it's a directly connected route. Now, if we take a look at the prefix 4444, this route has or was learned via EIGRP. And as a matter of fact, it comes with a whole bunch of information here. So number one, it comes with an administrative distance of 90. As we've learned, it has an administrative distance of 90. This value here is the feasible distance. The feasible distance is the lowest calculated metric to reach a destination network via its successor. And it has two successors. It can reach 4444 via Acme Edge 2, or it can reach it via Acme Core 1. And they're both equal load paths with the identical feasible distance. Now, let's take a look at how these prefixes were inserted into the routing table to begin with, okay? So if we go back here and I show IP EIGRP topology, let's focus first on loopback interface 1111. If it is directly connected, why is it part of the EIGRP topology table? Simple answer. I wanted the loopback addresses to be advertised into EIGRP. So to do that, I actually had to run this command, 1111. And on Acme Edge 2, network 2222. And on Acme Core 1, network 3333. So what I've done is I've inserted this loopback address and populated it as part of the topology. And that's one of the reasons why we're seeing it here. So this piece of information here is not relevant to the actual local router because he's directly connected to it, but it's meant to help other routers reach that loopback. And as a result, it's created a feasible distance of 128 to 56. Now, when Acme Edge 1 communicates with Acme Edge 2 via the EIGRP update packets, it's going to advertise, okay? It's going to advertise this feasible distance value as an advertised value. See, the feasible distance of the local router, which happened to be Acme Edge 1, all right, is the advertised distance when it reaches on Acme Edge 2, all right? Now, what happens is that Acme Edge 2 then calculates its own feasible distance to reach the 1111, and if the feasible distance is higher than the remote distance or the advertised distance, it is said to have met a feasible condition. See, the advertised distance has to always be lower than the feasible distance of the local router. All right? And if that is the case, it has now met a feasible condition, which means that it now has a feasible successor. And to reach this 11111 network, it reaches it via its directly connected link, which is 10.100.101. So if I do a show IP route here, I can see that 1111 is now learned via EIGRP from its neighbor Acme Edge 2. All right. Now the same thing goes for the next set. So now the feasible condition of Acme Edge 2 is going to be populated to Acme Core 2. So if I go to Acme Core 2 and I do show EIGRP topology, I'm expecting that the update that I receive from Acme Edge 2 is of the same value, and it is 130.816, 130.816, to which I apply, or this particular local router, Acme Core 2, then applies its own dual algorithm, and if its feasible distance is higher than its advertised distance, then it has now met its feasible condition, which means that this particular route via this successor is a valid path to be inserted into the IP routing table. Okay? And this is the way, and this is the logic that EIGRP uses to build its topology table, to build its routing table, and continues going down this path. Okay? So, if I was to shut down this link, and let's just say let's actually go here onto Acme Edge 1. I show, so I go config T interface very quickly, and I shut down this interface. So now this interface is shut down, even though it does show that it's up, it is down. Okay, and we go back to Acme Edge 1 and we go show IP route. You can see that that path is no longer a valid path, and the valid path now is via Acme Core 1. Okay, Acme Core 1. Now, having said that, if we take a look at we can also see that from two successors, there's now one successor. Okay, so if we go back to Edge 2 and we do a no shut, we let the routing protocol converge, you can see that it's repopulated itself because Acme Edge 2 has now notified Acme Edge 1 that this path is now up. So it's routing by rumor, right? This route, Acme Edge 1 does not have a purview of the whole autonomous system on its own. It relies on its neighbor to tell him when this link is up and when this link is down, which is, in my opinion, not a very good thing. There are other routing protocols that essentially give you the visibility, or give the local router the visibility to be able to make these assumptions on their own and give the router true autonomy on its own. And we'll get into those. I hope you enjoyed this video.